Swayam Prabha. Digital India. Educated India.
All right. So, good morning, good afternoon. We are in the series of lectures on analysis and design of rigid pavements, and I welcome all of you back. Today is a very exciting lecture because we are officially going to be going into Module 3. So, as a reminder, what is Module 3? Well, better question, what is Module 1 and Module 2 in case you've gotten a little out of sync with the class. So, Module 1 was basically an introduction. I told you that there are basically 4 types of rigid pavements that we're interested in. Jointed plain concrete pavements, JPCP. That's where we don't have any steel inside the concrete slab. We do have steel at the joints, that's for load transfer, but within the concrete slab, we don't have any steel reinforcement. JRCP, jointed reinforced concrete pavements, where we do have steel reinforcement inside the slab, and we also have steel reinforcement in between the slabs across joints. CRCP, continuously reinforced concrete pavement, that's where we don't actually have joints. We have a continuous stream of steel reinforcement going through the concrete, and it is characterized by a series of natural cracks which are formed at approximately 1 meter distance apart. And then PCP, pre-stressed concrete pavement, which are actually not constructed at site. They are made in a pre-stressed plant where an initial amount of pre-stressing is done. So the concrete doesn't start at a zero stress position. It starts in a compression position. So it's been pre-stressed. So then that enables us to, of course, have a stronger pavement in the sense that we can apply more load. It can bear more tensile stresses, but also we can just bring it onto the site and place it. So PCP is useful in specialized applications. It can get quite expensive to construct because after all, you have to build a separate plant, a pre-stressed concrete plant to construct these slabs. So it can get somewhat expensive to construct. JRCP is almost rarely used. You'll find very few examples of it in today's day and age. JPCP is by far the most widely used type of rigid pavements. CRCP is also used particularly in applications where we expect a very high volume of heavy traffic. Those are cases when CRCP might be a good option. So in these series of lectures, we have almost entirely focused on JPCP. We will look at CRCP briefly in Module 4 when we look at design procedures, but largely CRCP design is fairly similar to JPCP analysis and design. So although I'm emphasizing only JPCP in this series of lectures, understand that CRCP is going to track very closely up to a point, and beyond that point, we'll see in Module 4 what we can do. So that was Module 1 where we just had an introduction. Module 2 was on analysis of rigid pavement. So we're not doing design as of yet. We're still doing analysis. Analysis, long and short of it, we're trying to calculate the stresses in the pavement under a load. That's basically what we mean by analysis. So in the analysis of rigid pavements in Module 2, we looked at classical methods. Classical methods, in a way, means old methods. But what it actually means is methods which lead to a nice formula, a nice closed form expression, which we could do a hand calculation. We might use a digital calculator. Maybe we'll use a spreadsheet program, such as Excel or any other program, LibreOffice, LibreCalc, etc. But we definitely do not need to write any sophisticated programs in order to use those formulas. So that is why we call them classical methods. Classical methods have their limitations, however. There are several limitations that I discussed progressively, and therefore they don't necessarily always work. We do have a need for more sophisticated methods. In addition to looking at classical methods, so we looked at classical methods for calculation of stresses in the slab. There I introduced the very, very famous Westergaard solutions for a slab, where you can have a slab which is being loaded at the interior, slab which is loaded at the edge, and slab which is loaded in the corner, and Westergaard gave us solutions. We also looked at some updated solutions from Westergaard's theory, which make slightly different assumptions or correct some errors we made in Westergaard's theory. So we get somewhat different calculations from there, and we went through examples for that. We also looked at the effect of dowels, where for dowels we learned Freiberg's theory. We learned how to calculate the maximum bearing stress that the bearing stress that a dowel applies on the adjacent concrete, and what is the failure criteria in terms of the maximum allowable bearing stress on the concrete on the leaf slab. So we saw Freiberg's theory and analytical methods to do that calculation for a single dowel. And then we also saw what we can do when we have a family of dowels or a series of dowels, which is the actual case which we have in practice. We concluded module 2 by looking at climatic effects. So we saw what is the effect of climate, and by climate we basically meant temperature and moisture. So what is the effect of temperature and moisture on the performance of rigid pavements? We derived some closed form solutions for temperature distribution. So we saw how a nonlinear temperature distribution can be decomposed into a constant, a linear, and a nonlinear component. And for each of those components, we saw how we can calculate stresses. We also saw that for shrinkage, we basically get a nonlinear strain distribution, which we convert into some kind of fictitious or equivalent nonlinear shrinkage temperature distribution. Again, there's no such thing as a shrinkage temperature, it's just a fictitious number that we use for calculations. And since it's some sort of a temperature, we use the same techniques which we developed for actual temperatures to do the analysis for them and calculate equivalent temperatures. So with all of that and with several solved examples, we went through module 2. Module 3, which we're going to start now, is on the analysis of rigid pavements using the finite element method. Now, I should point out that the finite element method is not something that you can learn in 2 or 3 lectures. It's actually a very, very large topic. There are people who make their entire careers studying the finite element method. It is an exceedingly useful technique which is used almost universally in civil engineering today, in all applications of civil engineering. Very, very useful technique. It's on the face of it, it's actually quite an easy method, but it can seem a little bit daunting because generally we have very large equations and very large expressions that we're working with. So it can feel a little bit daunting to use the finite element method. However, the truth to understand is that when it comes to the finite element method, in classical methods, we had closed form solutions when we were solving examples by hand. But when you get to the finite element method, you actually don't solve them by hand. Yes, you could do some test problems in class in order just to learn the principle. But in practice, we do use a sophisticated computer program almost always to do calculations using the finite element method. So we will see fewer examples in module 3. I will show you examples where we're using software to do certain calculations, and we'll see certain benefits of doing it from the finite element method, which otherwise may not have been available from other methods. But today's lecture, when we're just starting out on module 3, I actually want to still talk about one particular analytical procedure which is still relevant enough to say it's part of module 3, but it is still analytical in nature. It will be useful for us when we go into the finite element method proper. And that particular method is for multi-layered rigid pavements. So when we talk about multi-layered rigid pavements, what you may recall is in module 2, we studied the equation of a JPCP. In particular, the equation we studied was this one over here, where just this component, d del power 4 is equal to q, where d is what we call the plate stiffness. So this was EHQ divided by 12 into 1 minus nu square. E was the elastic modulus, H was the thickness of the slab, and nu was the Poisson ratio. That was D. So we had D del power 4 W is equal to Q. This was the Sophie-Germain equation. This was the equation of a medium thick plate. To that, when we add a Winkler foundation, that we assume that the slab is actually sitting on a dense liquid or a Winkler foundation, that's how we model the subgrade, then we add this correction term Kw. This is actually just the reaction force which is coming from because of the presence of these springs. So d del power 4 plus Kw is equal to Q. This was our governing equation, but this was the governing equation for slabs on grade. That is, when you have this rigid pavement slab sitting on top of the subgrade, this is the governing equation. And we've been using this governing equation throughout in our calculations. Indeed, it is this governing equation that Westergaard used to derive his solutions and further subsequent solutions. So far, we've only been focusing on this particular equation. But now, if you go back to module 1, one of the lectures in module 1, we had actually talked about the fact that a rigid pavement is also a multi-layered system. So it is seldom the case that the rigid pavement is a slab on grade. That is, the slab is sitting directly on the subgrade. If you recall from those lectures, and I hope you go back to those lectures and have a chance to look at it again, the JPCP section almost always has at least a base layer, if not a sub-base layer. So we'll definitely have the JPCP slab on top. But below that, we will usually almost have a base layer. So this is PCC layer. We almost will have a base layer. Sometimes we have a sub-base layer. It's not necessary, but depending on the application, we have it. And then below that, we actually have our subgrade, which is the dense liquid foundation. You may recall that the reason we have a base layer, we had talked about this in module 1, the reason we have a base layer is to provide a stable platform for construction. So in JPCB pavements, a vast majority of the stress is actually borne by the slab itself through slab action. The base layer takes a negligible amount of stress. This, by the way, is in contrast to flexible pavements where you have transfer through from contact transfer basically. So you have transfer from grain to grain. So every layer is actually contributing to load transfer almost equally. Whereas in PCC pavements, the surface layer is taking almost all of the load transfer. So the purpose of the base layer is not to provide strength or to bear the load of the pavement. The pavement surface can more or less bear most of the load itself. But what we have the base layer for is to provide a stable platform for construction. Because in order to lay the concrete on the soil, we first of all need a relatively flat, a relatively workable surface on which these large paving equipment can run in order to pour the concrete on in the first place. So that is why we have a base layer to provide a stable construction platform. And then the question I put here is, do we really need it? Pretty much yes. It's a practical consideration that you can't actually drive these heavy trucks on subgrade on soil directly. The soil becomes uneven, it becomes unstable. And so you do need a stable platform in order for these large construction equipment to drive on in the first place in order to construct. So for practical reasons, we do really need a base layer. So the question is then, given the fact that we have established that a rigid pavement is not going to consist of purely slab on grade, it is going to be at a minimum 2 layers on top of the subgrade. What can we do? Is there any way we can modify our theory so far, the Sophie-Germain equation with the correction factor for the subgrade? Is there any way we can modify the governing equation to take this multi-layer system into account, or do we have to start from zero? It turns out we don't have to start from zero. So today's lecture, I'm going to introduce the concept of the equivalent plate formulation. So we are going to see something called an equivalent plate, where our multi-layered pavement can be converted into an equivalent system which consists of just the slab on the subgrade, and then we can do all our calculations on that. Something I should add, that when we do this, we will have to make some assumptions about the interface. So when we have 2 layers, when we have the PCC base layer, the PCC surface layer, and when we have the base layer, you could have sub-base below that. But when we have 2 layers, we have an interface between the 2 layers. We have to make some assumption about the behavior of the interface in the particular theory that we're working on, and in general, to model this type of a multi-layer situation in all cases. We will see how to do this for both bonded and unbonded surfaces. So those are the two sort of extreme situations where you have perfect bonding or no bonding at all. We will develop expressions for equivalent plate based on both bonded and unbonded interfaces. You may recall, if you've taken a class and if you go back to the class on design analysis of flexible pavements, there also we have to make some assumptions about bonding in layered elastic analysis. So it's not very different. Only difference is we're not using layered elastic analysis, we're using plate theory. So our final function, our final expression will look different, but from a mechanics perspective, it's generally the same assumption that we're making. One more thing I should add before we go into any of the details. This equivalent plate formulation has no approximation beyond the assumption we are making about the interface. So we are making an assumption whether the interface is perfectly bonded or perfectly unbonded. Nothing is perfect in life. And we'll talk briefly what to do in case we have more realistic conditions. But besides this approximation that we have to make, the equivalent plate formulation does not add any additional approximation. So our solutions are still exact. We are not making any error in the equivalent plate formulation. So that's just something I wanted to keep in mind as we go through this. Okay, so going back to the fundamental question which we're asking for today's lecture, since it turns out that JPCP sections are always multi-layered, you will have at least the surface layer and the base layer on top of a subgrade. You may also have a sub-base layer. Can we still use this medium thick plate theory? there are two ways to answer this question. So let's say this is our actual pavement. We have this PCC surface, we have this base layer, and we have the subgrade below that. We have two options. One option is as follows. We could try to combine everything below the slab. So we could say that we have the slab, the PCC slab, and below that we have some Winkler foundation, right? It's not the same, it's not the subgrade. We have some equivalent Winkler foundation that has the same effect as having a base layer. And then now we get back a situation of having a slab on grade, which we know how to calculate. Another option is that we actually combine all our layers above the subgrade. So the base layer, PCC layer, maybe the subbase layer, we combine all of them into some kind of an equivalent layer still sitting on our usual subgrade. So two options, we could combine everything below the surface layer, or we could combine everything above the subgrade layer. If we do the first option, then we will be creating some type of a composite subgrade. And in the second option, we will be creating some kind of an equivalent plate. As it turns out, the first option is actually quite difficult to use. Why is it difficult to use? Well, how would we even go about measuring this so-called composite subgrade? So if it's a subgrade, which we're modeling as a Winkler foundation, it's going to be characterized by some K value. How would we go about even measuring this value? If you recall, the test used to conduct the test which we conduct to measure the coefficient of subgrade reaction or K value for the subgrade is the plate load test, PLT. Please go back to module 1. We had a discussion on this in one of the lectures. So we use the plate load test in order to measure this K value. Well, as it turns out, it's quite difficult to use this test to get any sort of equivalent K value when you have a series of aggregate layers. A lot of variability comes in. So you might think it's as easy as, let me throw some aggregate layer, maybe a base layer, let me put it on top of a subgrade, and then I will construct the truss, etc., and I will do a plate load test on this. It turns out this leads to quite a lot of variability. It's not very easy to get a unique solution, and that variability can in turn have very large effects on our stress estimation in JPCP sections. So although this seems like a relatively easy, albeit empirical method to do, it turns out it can lead to quite a lot of errors in the calculation. So historically, we do not use this particular technique for JPCP sections. The second approach, which is the equivalent plate approach, is actually what's used in practice. And therefore, in today's lecture, I'm going to take you through the equivalent plate approach. I again emphasize the equivalent plate approach, except for the approximation we have to make in terms of the interface condition, that we have to assume some kind of idealized interface condition. Except for that approximation, there is no other approximation which is made. The equivalent plate concept gives us exact values of stress, as though we were actually calculating it for two layers. No additional error is accumulated when we use the equivalent plate concept. That's an additional value of using the equivalent plate. So the main paper from which I'll be taking a lot of this is this paper over here. This was from a very popular journal. Those of you who are a little bit more advanced students maybe have heard this journal called Transportation Research Record. It's a US-based journal, extremely good journal. The paper is called Structural Evaluation of Base Layers in Concrete Pavement Slabs. So structural evaluation is just a way of saying calculating stresses of base layers in concrete pavement system. So immediately when you say there's base layer, well, if it's a concrete pavement system, you have to have a surface layer. That's why it's called concrete pavement. And base layer automatically tells you we are talking about a multi-layered system in this case. So basically what this paper is, structural evaluation is to be read as calculating stresses. Base layer in concrete pavement system is basically saying that it is a multi-layered system. So really what this paper is doing, very succinctly in the title it says, calculating the stresses for multi-layered rigid pavements. And that's why I'm going to use this paper as a reference. This, by the way, is 1992. Not very old, it's around 30 years old. Not extremely old, not very new either. But compared to the fact that Westergaard is around 100 years old, definitely more recent than Westergaard. So here is the principle of the equivalent plate method. Before I go into all the formulas and calculations, I want to just give you what is the principle. The principle is as follows. If we have two plates in this case is the surface layer, so the PCC and the base layer. We assume both of them are plates. So that's one assumption which is made. The principle is that if we have these two plates and these plates are always in contact with each other, then we can replace it with a single effective plate that has the same deformation as the composite system. Okay, let's break that down a little bit to further understand it. So, drawing I drew up on the top over here, we had these two plates. If I take at any point, remember that if I can calculate the displacement W at any point. And because I'm assuming it's a plate, the displacement on the top surface is equal to the displacement on the bottom surface is equal to the displacement throughout, because the plane section will always remain plane. So I can just say that I've got at the mid plane, I've got a W1 for the top layer, and then for the base layer, I've got a W2. Because these two are always in contact with each other, that is, we don't allow any gap to form between the two layers, we can write W1 is equal to W2. This is always going to be true as long as we don't allow a gap between the two layers, which is generally the assumption we always make in our analysis. There are ways to overcome this assumption also, but that requires the finite element method. We'll see that several lectures later. So what we say is, suppose the equivalent plate theory has the principle that let us replace these two plates with one single plate. We have to figure out the properties of that plate, but which is what we'll talk about. But we replace it with a single plate whose displacement is some WE. So we call this an effective plate, and then it has a deflection of WE. The assumption we make is that WE is equal to W1, which is anyway equal to W2. So we have to find such a plate which for the same load gives us WE is equal to W1 is equal to W2. Now, what do I mean by find such a plate? Recall that every plate is basically uniquely defined by its plate stiffness. So two plates are the same if they have the plate stiffness. So plate stiffness is EH cube divided by 12 over 1 minus mu square. I hope all of you are practicing and you're able to write this formula. It's a very, very fundamental formula. It should just be this, and the radius of relative stiffness should be on your fingertips. You should know how to calculate these and write out the formulas. So this is the plate stiffness. So what we have three properties over here. We have E, we have H, and we have mu. That is the elastic modulus, the thickness, and the Poisson ratio respectively. So we have these three values. So when we say that we want to find an equivalent plate, that basically is saying we want to find what is the value of E, H, and nu for the equivalent plate. So if we say that plate 1 has E1, H1, nu 1, and plate 2, which is the base, has E2, H2, and nu 2, we are trying to find EE, where the subscript E refers to equivalent, EE, HE, and mu E. We need to figure out what these values are. Now, one common assumption which is made, it's not a necessary assumption which has to be made. There are ways to overcome this assumption. It's not actually very difficult, but a common assumption which is made, including the paper which is forming the base of our discussion today, is that all layers have the same Poisson ratio. It's somewhat of an odd assumption today. The truth is, when the paper was developed, it was difficult to measure Poisson ratio. So it was relatively straightforward to just make an assumption that they're all equal. There are ways to overcome it, but we'll stick to this assumption for now. So what we're saying is we assume that nu 1 is equal to nu 2 is equal to nu E. So we just take the Poisson ratio out of this. We assume that as a material property, our PCC layer, our base layer, and our equivalent plate, whatever that is, all have the same Poisson ratio. So we'll take one factor out of this calculation. Okay, with that, what we seek then, so nu E we are not concerned with. We already know its value is equal to nu 1, which is equal to nu 2. So what we have to calculate is, we have to calculate EE and HE. But after calculating EE and HE, we using certain theories, and we'll see an example of this in the next lecture actually. But using this, we can calculate some sigma E using whatever theory we had. So once we have an equivalent plate, once we have a load, we know how to calculate the stress. You can use Westergaard's theory or whatever other technique. Question for us is, how do we go back? We don't want sigma E. We want sigma 1 and sigma 2. We don't want the stress or the critical stress in the equivalent plate. The equivalent plate is just a mathematical fiction that we've created so that we can go back and use Westergaard solutions on the Sophie-Germain equation. We want the stresses on the real plates, on the real layers, which is the PCC layer and the base layer, that's sigma 1 and sigma 2. So not only do we seek to calculate the equivalent modulus and the equivalent thickness of the equivalent plate, we also seek a way by which we can recover the stresses of the original system from the equivalent system. And that's what we'll see the formulas to do that today. But before we do that, we have to make some assumption, as I mentioned, about the bond condition. So we have two layers over here. We have to say something about the bond in between them. There has to be some assumption we make. And the two simplified assumptions which we make, these are idealistic assumptions or idealized assumptions. But the two idealized assumptions we make are unbonded and bonded. What unbonded basically means is the deflections are continuous. So W1 here is going to be equal to W2. That's always the case. So W1 is always going to be equal to W2. But the stresses need not be continuous. That is, you can have a discontinuity in the stress at the interface while you still have continuity with the displacement. So unbounded condition means that at the interface, the stresses are discontinuous while the two layers are always in contact, so the displacements are continuous. Bonded, then we overcome that limitation. We say that the deflections are continuous. Deflections are always continuous. You'll always have W1 is equal to W2 if we don't allow a gap to form, which generally is the assumption we go with. But we also assume that the stresses are also continuous. Now, these are mathematical ways of putting it. Stress is continuous, stress is discontinuous. What does it mean in practice? What it basically means is if we have two unbonded layers, both are bending, both are undergoing flexure, they're undergoing flexure independent of each other. That is, the stress in one is not being affected by the stress in other, and they have two independent values of stresses. Whereas when they're bonded, the two are behaving as one single layer and they are bending together. So the bending of one plate is affecting the bending of the other plate. As you can imagine, these are very different assumptions. That two plates are bending independent of each other, only with some contact in between them, versus the two plates are behaving as one plate is bending. These are two very different assumptions, and so we get two very different formulations out of each of these, which we'll proceed to see right now. So we'll start with unbonded layers, basically because it's much easier calculation, it's much easier to understand. Now with unbonded layers, you want to recall that for any plate, unbonded, bonded otherwise, but for any single plate, we had derived that the moment m, and this can be mx, my. So that's why I just put this m dot. It's whatever, it's mx or n by mxy, it doesn't matter. The moment in each plate, you will recall, was some function of d, which was the plate stiffness, into some function of w. So this was some f of w. Okay, so you will recall that was the case for individual plates. So therefore, what we could always write is that m1, so the moment in plate 1 is d1 into some f of w1, and m2 is equal to d1 into some f of w2. Now, what we have is that for an unbonded layer, we must have continuity in our displacements. In other words, WE should be is equal to W1. W1 will always be equal to W2 because we assume full contact. So this condition has to be satisfied. It turns out the only way this condition is satisfied is if the equivalent moment on the equivalent plate is the sum of the moments on the original plates. In other words, ME is equal to M1 plus M2, which means we can write DE, which we don't know what DE is yet. DE into some function of WE is going to be equal to D1 into some function of W1. I just changed it. I mistakenly wrote this as D1. I just changed it to D2 plus D2 some function of W2. Furthermore, since we said that WE is equal to W1 is equal to W2 and the function which we are applying is the same, these three are all the same, they cancel out. So we get, based on this assumption, we get DE is equal to D1 plus D2. That's a pretty fundamental formula which we get for the unbonded layers. Now what we do in this case is we choose layer 1 as a reference layer. The way we do in equivalent plate theory is we always choose a reference layer which is an arbitrary choice. We have two layers. We can choose any of the layers as a reference layer. We can choose any other value also as a reference value. It's typically used though that we take the top layer as a reference layer. So we have the choice of a reference layer. So we have ME is equal to M1 plus M2. I can simply rewrite this as M1 into 1 plus M2 over M1. And then substituting that formula again, I can get ME is equal to some DE into 1 plus D2 over D1 into M1. Okay, there's no D here, this is just M1. So ME is equal to 1 plus D2 over D1 over M1. where d2 over d1, remembering that d is EH cube divided by 12 into 1 minus nu square, and nu is constant, so it's the same value for nu1, nu2, and nu3. What we then get is that d2 over d1 is E2, so this term is equal to E2H2 cube divided by E1H1 cube. The nu square, 1 minus nu square cancels out, 12 is just a constant. Okay. We also had that dE is equal to d1 plus d2. I already proved that. And so we can write EE is EE into HE. We have to calculate what EE and HE are. EE into HE cube is equal to E1 cube into H1 cube plus E2 cube into H2 cube. So these are the two sets of formulas we have. ME is equal to 1 plus D2 over D1 into M1, where D2 over D1 is equal to this expression over here. And we also have this EE HE cube is equal to this function of known values. It is always true, we assume that we have a rectangular cross section of our slab, and that's always true for JPCP. You may recall from your solid mechanics classes, if you have a rectangular cross section, then sigma is going to be proportional to m over h square. And so we will use this formula in order to calculate stress. But first, we have to figure out what is EE and what is HE. What is the equivalent modulus? What is the equivalent thickness? All right, so let's look at how we get EE and HE. Well, before we do that, what we can see is, because I wrote sigma is proportional to m over h square, then we can basically get these two formulas, that sigma E. So again, we had sigma is proportional to m over h square. And so sigma E is going to be proportional to me over he square. And so we can, and similarly, sigma 1 is proportional to m1 over h1 square. If we divide these two, so the proportionality constant goes away, we get sigma E over sigma 1 is basically equal to h1 square divided by he square into me over m1, where me, we already had a formulation for me over here. This was 1 plus d2 over d1 into m1. So if we substitute that, then we end up getting this formula over here. That is, sigma E is equal to h1 square over he square into e1 h1 cube plus e2 h2 cube divided by e1 h1 cube into sigma 1. But you will note we had previously defined this e1 h1 cube plus e2 h2 cube as ee he cube. So this formula which we have down here is a succinct relationship that if we could somehow calculate sigma E, for which we have to calculate EE and HE. We haven't talked about how to do that yet. But if we had some EE and HE, and if somehow we could calculate sigma E, which you can use Westergaard's theory, for example, then we can quickly calculate sigma 1 out of that. Okay. So then finally, what we make one assumption. So again, we have to somehow calculate EE and HE. It turns out we cannot independently calculate both. And truly speaking, we don't need to. We only need the relative value. We don't actually need the independent value. As you see throughout in these calculations, we always had ratios. We never had the values on their own. So really what we can do is we can choose one of EE or HE as a completely arbitrary value. You can choose whatever you want. We can choose one of them as an arbitrary value. Obviously, then the one equation we have, which is this equation over here, that EE HE cube is equal to this function of E1 H1 and E2 H2. If we choose one of EE and HE as a completely arbitrary value, then the other value is fixed by this equation. In practice, it is common to choose EE is equal to E1. That is, the elastic modulus of the equivalent plate is equal to the modulus of the first top plate. We can make any other assumption. You could assume EE is equal to E2. We can assume that EE is equal to E1 over E2 over 2. In fact, one of the exam questions I had given when I taught this class at IIT Gandhinagar a few years ago, one of the example questions I actually gave was basically exactly this. When I gave some other value, you can choose a completely arbitrary value. You could also choose HE is equal to H1. You could choose HE is equal to H1 plus H2. Again, it's totally arbitrary what you choose. The discussion we're going to talk about today, however, is EE is equal to E1. So we're going to stick with this because the paper, which is our reference, uses this. When this is the case, then what we basically get is E1 HE cube is equal to those terms on the right hand side. That was E1 H1 cube plus E2 H2 cube. We can slightly simplify this, that we basically want to calculate HE. So HE is going to be, we divide both sides by E1. HE is going to be H1 cube plus E2 over E1 H2 cube root. Common mistake I see students make, they forget to take this cube root. They just assume any radix sign is basically a square. So it's a cube root in this case. So if we make this assumption for the equivalent plate stiffness, then this is the value we are supposed to use for the equivalent plate thickness. Now, therefore we have, for the equivalent plate, we have the modulus and we have the thickness. Nu, again, we assume that nu is equal to nu1 is equal to nu2. So now we have completely defined our single equivalent plate. Now that we've completely defined it, we can use maybe Westergaard's theory or whatever to calculate the stresses when some external load is applied to it. That means using this theory and using Westergaard's theory or any other theory which is applicable, we can calculate sigma E under a load. Sigma E here, I mean equivalent stress. I don't mean stress at the edge. It's a little confusing because the subscript is the same. So previously we used sigma E to describe the critical stress when the load is at the edge. In this chapter, I mean sigma, in this slide, I mean sigma E as the equivalent stress in the equivalent layer. So please don't get confused by this. When we see an example in the next lecture, then I'll try to have a notation which clearly differentiates between them. Anyway, so once we have sigma E, now if we go back to this formula over here, we had this relationship between sigma E and sigma 1. Again, we want to calculate sigma 1. So in this relation, if we simply had EE is equal to E1, then we can cancel both of these out. And then we can do a further simplification from which we ultimately just get sigma 1 is equal to H1 over HE into sigma E. Furthermore, what we already wrote in the past based on this relationship that sigma is proportional to m over h square. So we can write sigma 2 divided by sigma 1 is equal to m2 over m1 divided by into h1 square divided by h2 square. And m1 and m2, we already said that m1 is basically going to be equal to d1 into some function of w1. Similarly for m2, the function is the same. W1 is equal to W2. So this really just turns into the ratio of D2 over D1 into H1 into H2, H1 square, H2 square. And so you can simplify it and you'll get this formula. Sigma 2 is equal to sigma 1 E2 H2 divided by E1 H1. For the sake of now, I'm not going into every detailed calculation of this, but I hope I've explained to you the procedure to get this formula in a simple way enough that you can do this on your own. Please do this calculation, please do this derivation on your own. That's the only way you'll fully understand what exactly we're talking about. Okay, so then what we have is, if we can solve for this equivalent plate, so we have derived the formulation for the equivalent plate, that is, we know the elastic modulus, the thickness, and the Poisson ratio for the equivalent plate. Then we can use Westergaard's theory or some other theory to calculate the stress on the equivalent plate for a given loading. And from there, we can calculate the stresses on the original system, the two-plate system, using this theory. So now we have a complete theory, and in this case, the only assumption we made was that we have unbonded layers. Beyond that, the fact that we chose EE is equal to E1 is an arbitrary choice, but it doesn't have any meaning, in the sense we can choose anything else and our equations will still set themselves to an equivalent value. So we'll still get the same answer regardless of what assumption we make. So that's how we calculate these values for unbonded layers without any error besides that one assumption. Let's also look at bonded layers. We'll do a solved example in the next lecture. So I just want to take you through the formulation in this lecture. Let's look at what happens when we have bonded layers. Now, when we have bonded layers, I said previously, when we have bonded layers, the two layers are not acting independently. That is, we have two layers, but there is no M1 and M2. So it's not the case that some moment is being applied on the first layer and some moment is being applied on the second layer, and the two remain in contact, which is how we get equilibrium. That's not what's happening in this case. When we have two different layers, then we actually have one equivalent moment which is acting on those two layers. And that equivalent moment cannot simply be written as the sum ME is equal to M1 plus M2. So it is not, this equality does not hold true in the case of bonded layers. Indeed, what happens is that the two layers actually have a common neutral axis. So previously, when we had these unbonded layers, I didn't draw it, but I'll draw it right now. The two layers actually have an independent neutral axis because they're unbonded. they're able to bend independently of each other. Now what happens is when we have two layers thus, right, which are bonded, so this is a perfectly bonded situation, then actually these two layers are going to have one common neutral axis about which they're going to bend. It's not going to be at half of the top layer or half of the bottom layer. It's going to be somewhere in between the two. For example, it could be, as I'm drawing, a little bit exaggerated, but I'm drawing over here. This is maybe the location where the neutral axis is. Generally, we'll show this with the symbol X. So X is not equal to H1 over 2. So the neutral axis is not the neutral axis of if it was just the first layer. It is not equal to H2 over 2. It's not the position of the neutral axis as though we had only the second layer. It's some value in between that we're going to have to calculate. So both layers actually have a common neutral axis, and all moments have to be defined from this common neutral axis. We do not have two separate neutral axes. Thus, the original two-plate system and the equivalent one-plate system must have the same neutral axis. So if I want to replace this two-plate system with a common neutral axis to an equivalent single-plate system that gives me the same amount of displacements and the same amount of stresses as the original system, then what I will have is my equivalent plate is going to have some thickness, but more importantly, it's going to have the same depth of the neutral axis as the original system, where depth is being counted or being measured from the surface. That is the fundamental assumption. Well, it's not an assumption, that's actually the fundamental corollary which comes out of a bonded layer system. So when we say the two layers are bonded to each other, it necessarily means that they have a common neutral axis. And so the equivalent plate, which is going to give us an equivalent amount, the same amount of stress, or pardon me, the same amount of displacement, is going to be such that it has some equivalent thickness, HE, is going to have some equivalent modulus EE. The Poisson ratio is still going to be the same, but the depth of the neutral axis is going to be the same as the depth of the neutral axis as for the original system. Very, very important result that we use for bonded layers. Okay. So, and this is a diagrammatic form of what I just said. So here we've got two layers and the neutral axis is at some depth X. This is the equivalent layer and the neutral axis is still at the same depth. So you see these two lines are aligned. These are still at the same depth X. X in this case for a single layer is going to be equal to HE over 2 because it's a single layer. But for the equivalent layer, X is not going to be equal to H1 over 2 or H2 over 2. We have to calculate it. In order to calculate it, first of all, we can use something called the parallel axis theorem. You may have, I'm pretty sure in high school, all of you studied the parallel axis theorem. So what the parallel axis theorem basically says is that we are trying to move the axis of a body from one axis to another axis. In that point, in that process, the stiffness of the body, because it's with respect to some kind of a parallel axis, actually the moment is also going to be shifted. So when originally for the individual systems, we measure the moment with respect to its neutral axis. But now because there is a common neutral axis, the total moment actually has to be with respect to the common neutral axis. So we have to shift the moment from the original neutral axis, which is at H1 over 2 and H2 over 2. Actually, it's H1 plus H2 over 2 because the depth is from the top layer. So these two original neutral axes, H1 over 2 and H1 plus H2 over 2, they have to be shifted up to the new neutral axis or the common neutral axis. In that process, the moment is going to get shifted. And when we perform that shifting then happens using the parallel axis theorem. The parallel axis theorem just says that we have E1 H1. E1 H1, you can say, is a measure of the stress or the measure of the moment inside the system. That has to be multiplied with the distance over which, the square of the distance over which the axis is being shifted. So if we consider layer 1, the original moment is E1 H1 cube divided by 12. Again, nu gets cancelled out everywhere, so that's why you're seeing just a 12 in the denominator. So it's E1 H1 cube divided by 12. Now we have to shift it by a distance which is equal to x. And so it is going to be shifted by x minus h1 over 2, wherever that is. So it's going to be E1 H1 into the square of the radius of gyration, which is x minus h1 over 2 square. For the second plate, we do have an E2H2, this slight typo here, this E2H2 cube. So we do, it's an E2H2 cube. So we do have this E2H2 cube over 12. That also has to be shifted to the position of the common neutral axis. And that is then going to be a shift of E2H2 into H1 minus H1 plus H2 over 2 minus x whole square. So that's how we use the parallel axis theorem to calculate the moment with respect to the common neutral axis. But then what is the common neutral axis? The common neutral axis can simply be calculated by equating the first moments of the area. So if we say in some measure the area of the stiffness or the mass of the layer is E1 into H1, then we equate the moments of it with respect to x, with respect to the neutral axis, and we'll end up with this formula. So here basically what we're saying is that E1H, so the moment of the entire system is E1H1 into A2H2 into the distance of the neutral, the depth of the neutral axis, that's x. That is going to be the moment of the first layer, E1H1, into its distance from its original neutral axis, H1 over 2, and similarly for the second layer. So when we are equating the first moments of area of the original layer with respect to their own neutral axis to the first moment of area of the two layers, but now with respect to the common neutral axis, that's how we calculate the depth of the common neutral axis. So this is how we calculate x. So we have x, and if we go back to this formula, which we get from the parallel axis theorem, we see that what we don't have is EE and HE. So we have x using using this particular formula by equating the first moments. But using the parallel axis theorem, we have x, but we do not have EE and HE. So we have one equation and two unknowns. We can't solve it. However, again, we can arbitrarily make a choice for either EE or HE. So similar to what we did for the first case, that is the unbonded layer, you can choose whatever you want. You can choose E is equal to E1, E is equal to half of E1, half of E1 plus E2. You can choose HE is equal to H1, HE is equal to H2, H is equal to the sum of H1 and H2, or any such combination. It's completely arbitrary. In the paper which we are forming on, as a general assumption which is also made, we assume that EE is equal to E1. If E is equal to E1, then we go back to this equation which we had from the parallel axis theorem. X again is known by equating the first moment of area. So what we get from the parallel axis theorem in that case is now we have EE. And so we can simply divide both sides by EE, which is equal to E1, and then we get an expression for HE. And that's the expression you'll get here. Note there is a cube root over here. Again, very common error that students make. You forget the cube root. So please don't forget to put that cube root. Your answer will be wrong. So when you do that, you'll get this as your expression. So we have HE is equal to H1 cube plus some E2 over E1 H2 cube plus 12 into x minus H12 whole square into H1 plus E2 over E1 into H1 minus x plus H2 over 2 whole square into H2 cube root of that. Okay, quite a mouthful. The only thing which I wanted to point out is if you wanted to check whether this expression was correct, did you make a typing mistake or something, again, just check if your units are consistent. So HE is going to be in mm. This term H1 cube is going to be in cubic mm, but you're going to take a cube root of it. So the final answer is going to come in mm. E2 over E1 is a ratio. There are no units. H2 cube, again, H2 cube root is going to give you mm. 12 is just a number. So x minus H1 over 2 square is in square millimeter, but it's being multiplied by H1, which is in millimeter. So this term is going to be in cubic mm. When you take the cube root, it's going to come out in mm. And then this again, E2 over E1 is a ratio. There are no units. H1 minus x plus H2 over 2 whole square. This is in square mm into H2. So that's cubic mm again. Take the cube root and you'll get back in mm. So you can just, although it's a fairly complicated expression, and when we do an example, we'll see how to calculate it, but you can evaluate these piecewise as we did in Westergaard solution. You can evaluate each of these four parts separately, add them up, and then take the cube root. That's how you make sure you don't get an error. Anyway, we will look at that procedure when we look at a solved example in the next lecture. Okay. And with that, then after we do all this, the stress can then be, the equivalent stress can be evaluated using this formula. So first of all, what we have is now we have an equivalent plate. In that equivalent plate, we have EE, which we just arbitrarily set to E1. And then we have HE, which you calculate using this sophisticated formula over here. So now we have EE and HE of the equivalent plate. So we have all the information. Nu E again is going to be equal to nu1 is going to be equal to nu2. There are ways to overcome even this assumption, but it's fine if you just stick to the assumption. So now we have completely defined the properties of our equivalent system. So that means if we now load our equivalent plate, so this is the equivalent plate. If we load our equivalent plate with some load, then using, say, Westergaard's theory or any other theory, we can calculate the stress, the critical stress, which is sigma E. Then, after calculating the critical stress, we can use this formula that sigma 1 is equal to sigma E into 2 into H1 minus X divided by HE. We can use this to calculate the stress in the original layer, which is sigma 1. Where did this formula come from? This formula basically comes from two, not assumptions, but two facts which we see in this. One is that the stress distribution is always going to be linear. That I think is correct. You can prove it mathematically. And those of you who've taken your solid mechanics classes for beam theory, which is pretty close to plate theory, it's just an analog of plate theory, the stress is going to be a linear distribution. One. And number two, the depth of the moment or the depth of the neutral plane of the equivalent system and the original system is the same. So here, if this is x, which happens to be equal to h e over 2, then we get the same x over here. These two are going to be the same. So what we are basically asking is, if in this case, let's say that using our Westergaard theory, we calculated the stress at the bottom over here, that is going to be at a distance of he. What we can do is then we want to calculate what is the equivalent stress in layer 1, and so we just have to scale it linearly. Because it's a linear distribution, we just have to calculate what would be the stress at a depth of h1. So that's the bottom of the first layer. So equivalent layer, we are getting the stress at he. In the original layer, we have to get what is the stress at h1, and so we just scale it linearly to calculate what that stress would be, and that's basically what this formula is telling us. So all this is saying is that sigma 1 is some linear scaling of sigma E. And you can calculate yourself, but this formula is pretty straightforward. Once we have that, we can similarly use this linear scaling and calculate sigma 2 if you want to. So that's then how we can use this concept of bonded layers to calculate sigma E, and from there we can recover the stress in the original system, sigma 1 and sigma 2. And all of that using this concept of equivalent plate, still using Westergaard's theory or any other theory that we have. Now, again, in the next lecture, we'll see a detailed example. I understand it was a lot of formulas, it was a lot of theory, so it would be good to go through an example. We will do that in the next lecture. Before that, I want to have a discussion on the only one assumption which is made in this theory. So again, if in this entire theory, with exception of one assumption about the interface, there are no approximations which are made. Our solution is exact. So if somehow we had an exact theory for two-layered systems or two plates, and we use this equivalent plate and compare it to the result of the analytical result of the two-plate formulation, we would get exactly the same answer. So there is no approximation being made in this case. The approximation is made in understanding what is the type of interface that we have. The question we should ask is, so if the layers are truly bonded or unbonded, that really we can say that the two layers are acting perfectly together, that they're bonded, or there's absolutely no interaction between them beside transfer at the interface, then if that is truly the case, then our formulation right now is correct without any approximation. We have not incurred any error whatsoever in doing any of this. But is this really the case in practice? Do we ever actually have a situation where we have perfect bonding or perfect unbonding? Or do we actually have a situation in real life where we have partially bonded interfaces? That's a question that we should think about as engineers. Now, without going into too much experience, it will take quite a lot of experience to answer the question, but even without the experience part of it, you can ask yourself, is anything perfect in life? Particularly in something like pavements, which there's so much variability in construction, there's so much variability in traffic and in climate. In these considerations, do we actually have an idealized case of perfectly bonded and perfectly unbonded? I think all of you will agree with me that this is not the case. Realistically, we're going to have some amount of partial bonding. That is, instead of the two layers acting totally independent of each other or being completely bonded and having a common neutral axis, the behavior is actually going to be somewhere in between these two, where part of there is some amount of interaction between the two layers. Part of the two layers are sharing their neutral axis, but there is also a component where the two layers are able to act independent of each other. So it turns out this actually is a realistic case, and we cannot analyze it using this theory that we specified. So then The question is, how do we analyze it in this case? How do we analyze a situation where we do not have perfect bonding, but we have partial bonding? As it turns out, there is a particular method to do. There is a third type of interface, which is called a Totsky interface. A Totsky interface is simply specified as a bed of springs. So what we have is, we have a series of springs in between, and these springs have some sort of stiffness which has been specified. So obviously, when you have these springs in between, if we specify the stiffness, say K, as tends to infinity, that is, we have very, very stiff springs in between, then we basically have a bonded layer. If on the other hand, K tends to 0, that we have very, very low spring stiffness in between these two, then that corresponds to an unbonded layer. 0 and infinity, of course, are idealized values. So what that really means is that we can analyze a partial bonded case using this type of an interface condition, where our two layers are actually connected by a series of springs. And this type of an interface, this spring interface between two layers, is called a Totsky interface. This name, by the way, is a Russian name. That's why it's spelled in this way. But but it's used quite widely in certain applications, which we will talk about later. So, if this is the case, if the Totsky interface is the quote unquote realistic condition, it's what should be analyzed. Why didn't I do that? Why did I take you through all this trouble of analyzing partially bonded cases, or fully bonded or unbonded cases? And similarly, in the next lecture, we'll do an example. Why are we doing that if we know Totsky interface is the more realistic case? The answer is difficult to obtain analytical solutions. So, Totsky interface is certainly a more realistic situation, but to solve a two-layer system like this using a Totsky interface, that is not an easy proposition to do. In fact, it cannot be done analytically. It needs to be done using the finite element method. So we will not discuss this in terms of a solved example now. When we go into looking at examples in the finite element method, which is only about one or two lectures from now, that's when we will revisit and see how a Totsky interface can be implemented. Okay, so with that, in today's lecture, I showed you a formulation for a multi-layered pavement system. That is, when we had two layers, depending on whether they're bonded or unbonded, we could combine them into a single equivalent layer that's sitting on top of a subgrade. For a slab-on-grade situation, we already know how to use Westergaard's theory or any other theory to calculate the stresses. And then we saw, after calculating the stresses in the equivalent system, how we can recover the stresses in the original system. There was a lot of formulas, a lot of maths involved, and I did not do a solved example. So in our next lecture, we'll actually go into the solved examples, and I'll show you how you can apply this to solve for a particular problem. So I will see you in the next lecture. Thank you.